Okay, so we're going to go over our first example, and I have the example sketched here. Here we have just a copper piping system, and it's a model of what you might have inside of your house, where at the basement or lower level of the house, you have a flow rate of water going in at 12 gallons per minute. It goes over 15 feet, turns through a 90-degree elbow, goes up to the second floor, or from the basement up to the first floor, up 10 feet, turns in a 90-degree elbow, goes over 5 feet, turns in another 90-degree elbow, goes up 10 feet, turns in another 90-degree elbow, goes to the right 10 feet, goes through a wide open globe valve, goes to the right another 10 feet, and then goes out through the faucet on your sink. Okay, and so the pipe is made out of drawn copper. Inside of the house, the diameter of the tubing is 3/4 of an inch, and the exit diameter of the faucet is 1/2 inch. Okay, and so we are asked to find what is the pressure in the basement of the house, basically right where the water enters the house, which is right here. So what is the pressure needed to drive the flow up to the second floor of the house and out through the sink? Okay, and so we have our geometry. This diagram here is kind of messy, so I'll do sort of a cartoony stick figure of the piping system. So it goes over 15 feet, up 10, over 5, up 10, over 10, globe valve, and then over 10, and then the faucet. So this would be 15 feet, 10 feet, 5 feet, 10 feet, 10 feet, 10 feet, and then the faucet. Okay, and you have Q going in. Okay, and so now what we are asked to find P in, that's the inlet. For A, we neglect all losses. B, we include major losses only. And C, we include major plus minor losses. Okay, and so what you'll see with this example after we complete it is that the viscous flow in pipes really makes a huge difference, even for this mundane run-of-the-mill pipe analysis. Okay, and so the assumptions. One, we'll assume steady flow. We'll assume rho and the viscosity are equal to a constant. Okay, we'll assume there's no leaks. And we'll assume that the atmospheric pressure equals 0. Okay, and I'm going to scroll up back to the picture again. Now, when you turn on the faucet, which is right here, and it goes into the sink, that water is exiting as a free jet. So we're going to assume that the water exits faucet as a free jet. Okay, and so here we might as well get some properties. And from the back of the book, for liquid water, you can assume, or you can find that a rho is equal to 1.94 slugs per cubic foot, and the viscosity, the dynamic viscosity, is 2.34 times 10 to the minus 5 pound-force second per foot squared. Okay, and so those are our, so we know those for our properties. We got those from the back of the book. And so the solution to this, based on our assumptions, we've assumed steady flow. It's incompressible because rho is constant, and then also mu is constant. So we can use the energy equation with the head loss form that I derived in the previous lecture. And so the solution, use the energy equation with a head loss. Because for this problem, we are explicitly being asked to account for viscous losses. So that in general is P over rho G plus alpha, which is that bogey correction factor for the kinetic energy, times the average velocity squared over 2G plus Z at the outlet of your piping system minus P over rho G plus that bogey correction factor times U average squared over 2G plus Z at the inlet, and that's equal to any pumping work going in divided by m dot G minus any turbine work going out divided by m dot G minus the total head loss. Okay, and so we don't have any pumps or turbines in our piping system, so that's gone. And so now, so immediately we've crossed out everything that we can cross out. So we're just going to go through and work through this equation here because we still don't know what alpha is and things like that. So let's just work at the inlet state and the outlet state and find out what the U averaged is and stuff like that so we can start putting in numbers. Okay, and so at the inlet, which is in the basement, we know that the area is equal to pi over 4 times the diameter squared. That equals pi over 4 times 0.75 inches times 1 foot per 12 inches squared, and we will need this actual length later, so that's 0.0625 feet. And the cross-sectional area of the circular pipe is 0.003068 square feet. Okay, then we know the cross-sectional area, and we know the average velocity, so U average, and again these are at the inlet state, that equals Q over A, and if you convert the gallons per minute to cubic feet per second, you find that Q is equal to 0.0267 cubic feet per second over the cross-sectional area, which is 0.003068 feet squared, and that gives a average velocity at the inlet state is equal to 8.70 feet per second. Okay? And we need to pick a datum, so I'm going to scroll back up to the cartoony picture. So I will choose the datum to be at the lower level. Okay, and then I'll label the outlet here. Okay. So Z1, since we are at the datum that is 0, at the outlet we go up 10 feet and then up another 10 feet. So we will need that Z later, and that will be 20 feet when I get to it. Okay? So Z in equals 0 because it's the datum. And then we need alpha. And alpha is either 1 or 2. And it is 2 if the flow is laminar in the pipe, and it is 1 or slightly greater than 1 if the flow is turbulent. So alpha, let's check the Reynolds number so that we know which one to use. Okay, and so RED equals rho times the average velocity times d over mu, and that equals 1.94 slugs per cubic foot times 8.7 feet per second times 0.0625 feet over the viscosity, which is 2.34 times 10 to the minus 5 pound force second per feet squared. And I'm going to convert the pound force to slugs and acceleration. So 1 pound force, lbf, is equal to a slug feet per second squared. And then if you punch in the numbers, you find that RED equals 45,000, which is well above 2,300. So this implies turbulent flow. Okay. And that means alpha at the inlet state is equal to 1, but because it's turbulent. Okay, and then also D of the pipe equals D of the inlet. So basically, this is the same Reynolds number for the entire piping system. And so basically, this diameter, this average velocity here, this diameter, and this Reynolds number are the same Reynolds number for the entire piping system, with the exception of the outlet at the faucet. But that's it. Okay. So we now know the alphas, the average velocities at the inlet. Now we got to do the same thing for the outlet state, and that's at the faucet. Okay, and A equals pi over 4 d squared, and that equals pi over 4 times 0.5 inches, and I'm going to convert that to feet, times 1 foot over 12 inches, that whole quantity squared, and because we'll need this length later on, that's 0.0417 feet. And so the cross-sectional area at the exit is 0.00136 square feet. Okay, and then the average velocity equals Q over A. So that equals 0.0267 cubic feet per second divided by 0.00136 feet squared. Okay, and that equals 19.6 feet per second. Okay, and I already argued earlier that Z at the outlet equals 20 feet. Okay, and now we need alpha. We need alpha. So again, check the Reynolds number. Because the diameter is different, we may be in a situation where maybe the Reynolds number is lower, and now it's laminar. So RED equals rho U averaged D over mu, and that equals 1.94 slugs per cubic foot times the average velocity here, 19.6 feet per second, times the diameter, 0.0417 feet, divided by the viscosity, which is 2.34 times 10 to the minus 5 pound force second per foot squared, times 1 pound force is a slug feet per second squared. Okay, and so RED, this equals 67,760, which is again greater than 2,300, which implies turbulent flow, which implies that alpha equals 1. Okay? And so now we have now quantified everything that we know about the inlet and the outlet states. So using this information, we have from the energy equation P over rho G plus alpha U averaged squared over 2G plus Z at the outlet minus P over rho G plus alpha U averaged squared over 2G plus Z at the inlet equals equals minus the head losses. Okay, well, we know that this is 0. We know that alpha equals 1. This is the inlet pressure that we are trying to solve for. In the elevation at the inlet is 0. We know that alpha equals 1, and we know that P equals 0 because it's a free jet. Okay, and so we're assuming that the atmospheric pressure is 0 here. Okay, so then we solve this for Pn for the pressure at the basement that's driving the flow, and Pn equals rho over 2 times the average velocity at the outlet, I'll just call that out, squared, and we found that, minus the average velocity at the inlet, I'll call that un, squared, plus rho g z at the outlet, which is the faucet, plus rho g times the head loss. Okay, and so all I did to get this was I just took this equation here and solved for the inlet pressure. Okay, and so above we calculated this, and we calculated this. So now we are just about ready to start putting in the numbers. Okay, so we are ready for part A actually. So for part A, no losses implies that the head loss is equal to 0. And I'm going to scroll up again, and this energy equation here that we have here, if the head loss is 0, this actually just turns into the Bernoulli equation if alpha is equal to 1. But however, the Bernoulli equation and this energy equation are derived on completely different principles, even though they look the same. The Bernoulli equation, remember, was derived from a momentum balance on a fluid element that is following a streamline. This equation here was derived from conservation of energy, and it was directly applied to a piping system that has all sorts of other details that are not included for in the Bernoulli equation. Okay? So even though the forms look the same, they come from completely different principles. So for no losses, the head loss is equal to 0, and we can just stick in the numbers that we computed above. And so the inlet pressure equals a rho over 2, 1.94 slugs per cubic foot divided by 2 times 19.6 feet per second squared minus 8.7 feet per second, and that whole thing squared, plus the elevation, that would be 1.94 slugs per foot, slugs per cubic foot, times gravity, which is 32.2 feet per second squared, times the elevation, which is 20 feet, plus rho g htl, and that's 0 because there's no losses here. Okay, and so if you convert the slugs to pounds force and all that fun stuff, which in your homework you should definitely show, you find that the inlet pressure in the basement that is required to drive the flow is equal to 1549 pound force per square foot, or that equals 10.76 psi G, and G means gauge. And so this is there are no losses. Okay, and this is and these losses here are this pressure here, I should say, is really just it is required to. I'll scroll up to the diagram again. It is required to actually take the water and basically elevate it up 10 feet, and then also accelerate it through the reduced area at the exit of the faucet. And so it just requires to basically 10 psi, a pressure difference of 10 psi between the exit and the bottom of the basement that is required to drive that flow if there are no viscous losses. But now for part B, we need to start including the viscous losses, and you'll find them to be substantial, not some minor little correction, but enormously important. Okay? And so B, for part B, will include the major losses only. Okay, and so remember that the total head loss is equal to the minor head losses plus the major head losses. And the major head losses are due to fluid friction along the walls of the pipes themselves, and the minor losses are due to losses through the various components, such as the elbows and valves and things like that that are in the system. So for part B, we are asked to only include the major losses, so we will forget about this until part C. And so for the major losses, that is equal to the sum of the Darcy friction factor times L over D times the average velocity squared over 2G. And this is applied to each section of the pipe. Okay? So here we have 6 sections of pipe. And I'll draw another little cartoon of that. So we have one section here, then the first rise at section 2. Oops, I don't know why my thing does that. We have the first section here, then the rise, which is the second section, then the second horizontal jump, that's section 3. The second rise, which is the fourth section, the 10 feet to the globe valve, and then 10 feet, and then that's the exit, and that's the exit through the faucet. And so this length here is 15 feet, this length here is 10 feet, this length here is 5 feet, 10 feet, 10 feet, 10 feet. Okay, and then one thing to note is that the diameter of the pipe is equal to 0.75 inches throughout this entire piping network, up until the very end through the faucet. Okay, so we essentially have 6 sections of pipe, but each have the same diameter as the inlet. So that implies for each section of pipe, that implies that RED equals RED of the inlet, and D equals D of the inlet, and U average equals U average at the inlet state. Okay, and you can, and then just be careful, because for some problems you could have maybe this section of pipe here for some reason has a bigger diameter. And so if that's the case, you would need to compute the Reynolds number for this section of pipe and the average velocity and all that stuff for that section of pipe, and then include it in this formal sum here. But here we have 6 sections of pipe, and U average, G, D, and F will be the same for all of them. Okay? And so F is the Darcy friction factor. And you can get that from the Moody chart. or solving the Colebrook equation. Okay, and in one of the previous lectures I showed you how to read the Moody diagram, so I'm going to show you how to solve the Colebrook equation. Okay, and so F here is a function of RED and the relative roughness epsilon over D. And epsilon, recall, is the surface roughness. Okay, and then on table 8.1, for various materials, you can find the surface roughness. So from table 8.1, for drawn tubing, epsilon equals, I got to get the number of zeros right here, 0.12345 feet. Okay? So we can get that. So then, the relative roughness, epsilon over D, equals 0.000005 feet, divided by the diameter, which is 3/4 of an inch, or 0.75 inches, times 1 foot per 12 inches. That implies that the relative roughness equals 0.00008. Okay? And RED, we already calculated that above, so that's the same as inlet. And that equals 45,000. Okay? So now, for all these sections of pipe, they have the same RED, the same epsilon over D. So in the sum for each section of pipe, F is the same, D is the same, U average is the same, and 2G is the same. So, and also from the Colebrook equation, the friction factor is a function of the Reynolds number and the RED, or and the relative roughness. So then we're gonna use the Colebrook equation to solve that. So the Colebrook equation states that 1 over square root of F equals minus 2 log base 10 times acting on the relative roughness divided by 3.7 plus 2.51 over the Reynolds number based on diameter square root of F. Okay, and we found the relative roughness. That's 8 times 10 to the minus 5, and we know that RED is 45,000. Okay, so we stick in the numbers, and we get that 1 over the square root of F equals minus 2 log base 10 of 2.162 times 10 to the minus 5 plus 5.578 times 10 to the minus 5 divided by square root of F. Now we need to solve this equation implicitly, and I described in an iterative procedure for doing that earlier. Here I'll show you how to use a Wolfram Alpha, because you guys should all have access to that, and so we will go through it that way. So we want to use Wolfram Alpha. I actually have the actual app on my iPad here. Okay, so we want to solve. That is with, as I described earlier, that's with the find root command. And you put the list of equations that you're solving in curly brackets. So that's 1 divided by the square root of our friction factor F. And to differentiate the left-hand side from the right-hand side in your list of equations, it's better to use a double equal sign, minus, and then you put in the right-hand side, that's minus 2 times log base 10, acting on 2.162 e to the minus 5 plus 5.578 e to the minus 5 divided by the square root of the friction factor. Okay, and now I close the log. close the bracket for the equation list, then do the list of variables. So that's f, and so we're solving for f, and our first guess we're going to just tell it to start iterating at 0.1. And assuming I input everything correctly, this should be able to solve it. Okay, and it looks like it did. So again, when you use Wolfram Alpha and you put in your command, check the input interpretation and make darn sure that it's doing it what you want it to do. Sometimes it will interpret things not the way you intended, and you just have to change the way that you input them. Okay, and so it looks like it's trying to find the root of this equation in the middle here, and it's solving for f, and the first guess is 0.1, and that is the correct equation, and we find that f is in the result box, and that is 0.02166. Okay, and so that's how we use Wolfram Alpha for that. And so solving with Wolfram Alpha, gives f equals 0.02166. Now, for your homework and even quizzes and things like that, you are more than welcome to use Wolfram Alpha, but with the solution, please attach a screenshot of the Wolfram Alpha command and the output, just to prove to me that you used it. Okay? So from Wolfram Alpha, we know that f is that. So we now know everything we need to know to find the major head losses. So HTL major equals the sum of the Darcy friction factor times L over D of the section of pipe times the average velocity squared over 2g. Okay, well, just about everything here is the same for all sections of pipe, FD and U averaged in G. So we can basically yank those out of the sum because the diameter of each section of pipe is the same. So that becomes F over D times the average velocity squared over 2g times the sum of the lengths of all the piping sections. Okay? Okay, and so now we're going to put in the numbers. And so this equals 0.02166, and f is unitless, divided by 0.0625 feet for the diameter, times the average velocity squared. It's 8.7 feet per second squared over 2 times g, which is 32.2 feet per second, times the sum of all the lengths. And so we have 15 feet for the bottom section, a rise of 10 feet, then we go over 5 feet, then we go up 10 feet, then we go over 10 feet again. Oops, and I keep hitting that button, sorry about that. And I go over 10 feet for the last time. And so this whole thing is 60 feet. Okay, and so if we in the units of the gravity are feet per second squared. I was wondering why this wasn't being unitless. So then this implies that we punch in the numbers. HTL major equals 24.83 feet. Okay. So then, for this case, P1 equals rho over 2 times U out squared minus U in squared plus rho G Z at the outlet, which is the faucet, plus rho G times the total head loss. Okay, well, we already computed this from part A, and that's 1549 pound force per feet squared, so there's no need to punch in those numbers again. So this is equal to, and Pn is equal to that, not P1, equals 1549 pound force per foot squared, plus the density, that's 1.94 slugs per cubic foot, times g, which is the acceleration, that's 32.2 feet per second squared, and times the total head loss, which is 24.83 feet. Okay, and if you punch in the numbers and convert this into pounds force, you will find that this term here adds another 1549 pound force per foot squared. Okay. Oh, not 1549, sorry about that, 1552. Okay, so basically, this just due to pure friction in the pipe walls, as the fluid moving through it, this is more than doubling the pressure that it takes to drive the flow from the basement up to the second floor. Okay, so then add those together, we get that P1 equals 3101 pound force per foot squared, and that equals 21.5 gauge pressure PSIG, and that's major losses only. Okay, so now that's including just the major losses. So now we need to do part C, and part C is the major plus the minor losses. Okay, and the minor losses, we already computed the major losses, so now we need to compute the minor losses. So the minor head losses, that equals the sum of the loss coefficient for every single component times the average velocity squared over 2g. So now I'll do yet another little cartoony diagram. We need to count up all the components and get the loss coefficients. Okay, and so now we sort of just we sort of go through the piping system and sort of make a bill of materials. So now count the parts. So we have a part, a quantity, a KL, and a source. And that sources, we are just listing where we got that from. Okay, and so in the problem statement, it's stated that the elbows are 90-degree threaded elbows. And we have an elbow here that turns the flow up, an elbow here that turns it over, an elbow here, and an elbow here. So we have 4 of those. Okay, and if you look at table 8.4, you'll find that the loss coefficient for a 90-degree threaded elbow is 1.5. Okay, and then above here, we have a wide open globe valve. Okay, and the faucet here, and 90-degree elbows, which are threaded. Okay, and so the second part is we have the wide open globe valve. We have one of those, and from table 8.4, that loss coefficient is 10. Okay, and essentially what a valve does, as you close the valve, it just increases the loss coefficient to where it becomes theoretically infinite. And so that's essentially how, if you want to model the action of a valve, you just need to find the loss coefficient as a function of the valve opening. And as the valve gets becomes more and more closed, the loss coefficient will basically start skyrocketing in a nonlinear fashion. And then there's the faucet. And in the instructions it says U averaged is based on the pipe velocity. So if you have a reducer or an expander and a vendor gives you a loss coefficient, they will often tell you how basically what velocity that loss coefficient is based off of, whether it's the velocity in the small area or whether it's the velocity of the fluid in the larger of the two areas. Okay, and so in this case we were told it's based on the pipe velocity, which would be the average velocity that we've been using most of the time. And that loss coefficient is 2, and that was given in the problem statement. Okay? And also all parts in the pipe have U average equals 8.7 feet per second. So then the HTL, or the minor head losses, equals the sum of the loss coefficient times U averaged squared over 2G. Well, because for all the components, including the faucet, the average velocity is the same, we can pull that out of the sum, and that equals U averaged squared over 2G times the sum of all the loss coefficients of our components. And so now we just literally add those up. And I'm going to punch in the numbers now. So that equals 8.7 feet per second squared over 2 times 32.2 feet per second squared times the sum of the loss coefficients. And we have 4 elbows. I'm going to scroll up here a little bit. We have 4 elbows, and their loss coefficient each are 1.5. We have one wide open globe valve with a loss coefficient of 10. And we have the faucet, which has a loss coefficient of 2. Okay, and if you punch the numbers in, the minor head losses are 21.16 feet. Okay, so then Pn equals the same formula that we've been using, rho over 2 times U out squared minus U in squared, plus G Z out, plus rho G times the minor head losses, or the major head losses, sorry, plus rho G times the minor head losses. Okay, and we already computed this. This here was 1549 pound force per square foot. We computed this. This was 1552 pound force per foot squared. And the sum of these two was 3101 pound force per foot squared. Okay, so then P in equals 3101 pound force per foot squared plus rho 1.94 slugs per cubic foot times G, which is 32.2 feet per second squared, times the minor head losses, which is 21.16 feet. Okay, and if we punch in those numbers and convert it to pound force per foot squared, which in your homework I expect you to do, that equals 1322 pound force per foot squared. Okay, so then P in for this case is equal to 4423 pound force per foot squared, and that equals 30.7 psi gauge pressure. And that's the minor plus major losses. So that's the major plus minor losses. So the minor losses are not so minor in this case. Okay, in that they basically, if you included the minor losses only and neglected the major losses, again, you would about double the pressure that is needed to drive the flow. And so I'm just going to finalize the results in a table. So we have Pn equals, in the basement, 10.76 psi gauge pressure, and that's no losses. And that's the value you'd get that if you chose incorrectly to use the Bernoulli equation for this, you would get the 10.76. However, if you include the viscous losses, you get 21.5 gauge pressure, psi, and that's only the wall friction as from the wall shear stress as the fluid flows through the pipe only. And if you add the fluid friction as the flow gets turned and goes through all the components, which are the minor losses, you get 30.7 psi gauge pressure. So that's major plus minor losses. Okay, and so you can see that clearly that the viscous losses, or viscous effects, or viscous losses, have a huge effect. Okay, and in many cases for pipe flows, you cannot neglect the viscous losses. Okay, even though we've been using the Bernoulli equation for long sections of pipe and not including the viscous losses, that was really just to get you guys practiced using it. But in reality, for a piping system, you normally cannot neglect the viscous losses.